Hello, my name is Sarah Downs, and today I'm going to talk to you about simulations of pulsing soft corals. The corals that we're working on modeling are these xenid pulsing corals, which are seen in the video here. What makes these animals unique is that they pulse to mix the surrounding fluid, but this pulsing isn't used for locomotion or food capture. So biologists are trying to understand why exactly they pulse, and one of the leading hypotheses is that it is used to increase photosynthesis for their symbiotic algae. But with this, we are still trying to understand how these corals are pulsing and mixing fluid and their role in coral reef ecosystems. So this leads us to the goal of my project, which is to simulate the fluid structure interaction between these corals and the fluid they're mixing using the immerse boundary method for a full 3D coral simulation. And then once we have this, we'd like to analyze the resulting fluid flow and mixing that occurs. So our coral movement and resulting fluid flow are modeled using the immerse boundary finite element method. In the figure here, we can see live corals as they are pulsing. And so what we have is that we define our boundary, which is actually going to be the body of our coral using a Lagrangian framework. And then we define the fluid, which is the rest of our environment, using an Eulerian framework. We then couple these two frameworks using our interaction equations. And something to note is that, like, we have these images of live corals here. All of our data that tells us how our coral is moving is actually coming from live coral data. So we're working within a realistic environment. Okay, so now over the next few slides, I'm going to tell you a little bit more about this frameworks and how we're actually setting up these models. First of all, our fluid flow is modeled using the Navier-Stokes equations for viscous incompressible flow. In our first equation, we have our conservation of momentum, and then in the second, we have our conservation of mass. And here our variables are P, which is our fluid pressure, U is our fluid velocity, F is our force applied to the fluid by the corals. So this is the force that occurs from when the coral is moving. And then we also have rho, our fluid density, and mu, our fluid viscosity. And what we're trying to solve for here are P, our fluid pressure, and U, our fluid velocity. And one thing to note, like I've mentioned, we are working in full 3D simulations. So every variable that has a bar under it is actually going to be a 3D vector. Next, we have our interaction equations. So these are used to help us convert from Lagrangian to Eulerian variables and vice versa. We start by knowing our force, which is going to be our big F, in our Lagrangian framework. And this is defined as the summation of our target force and our elastic force, where the target force is the force that comes from prescribing the coral's motion, which again, that prescription of the coral's motion comes from actual live data that we have. And then the elastic force comes from the elastic body forces of the coral. So what we do is we use our Lagrangian force to find our force in the Eulerian frame. We then solve for the velocity in the fluid and interpolate to move the coral, and then work back into the Lagrangian framework. So what we're doing is we start in the Lagrangian framework, we go to the Eulerian framework, and then we go back to the Lagrangian framework. And this all happens for one time step. So this also leads into our immerse boundary finite element configuration. So if we start in our reference configuration X, which is just a single point, we then deform or move, which gets us to our current configuration chi. Now this deformation gradient in chi is going to be used to help us calculate our forces. So this is just an important piece of everything that comes in. Now all of this is actually solved using the IBFE library, which is a part of the IBAMR library. And so here our Navier-Stokes equations are solved on an adaptive Cartesian mesh using a finite difference method. And we can actually see this adaptive Cartesian mesh here, where this red outer box is our whole fluid domain. And then as we get closer to the coral, we start working on finer meshes. And here we can actually see the coral in the smallest light blue box. So that's the small figure here. So what this tells us also is that we're working in a large fluid domain compared to the size of our coral, but it helps us get a sense of how fluid is moving both close and far away from the coral. Then the tentacles are discretized using a finite element method. And we can see the mesh for that here, where we have our mesh is created of uniform triangular mesh. And then our interaction equations are solved using Gaussian quadratures. Next, I just want to tell you a little bit about our coral kinematics. So like I've said, the kinematics are prescribed using our target force, which is the force that comes from prescribing that the coral move in a specific way. And again, this is coming from actual live data. So our F target is a generalization of actual motion. And here we have 3 phases of motion. We have rest, where the coral is just sitting still, and that can be seen here. So this rest happens for about 0.8 seconds until the coral begins to contract. So it moves in an upward motion until the coral tentacles are fully up. So this contraction takes about 0.7 seconds in total. And after that, the coral begins to expand. So this is this last phase of motion. And then once it gets back down to the resting position, it restarts. So that makes up an entire pulse, where this whole pulsing period takes about 2.4 seconds. And something else to note is that we're working in a Reynolds number of 61.7, where our Reynolds number is our ratio of inertial to viscous forces, and the length of our tentacle, so the length of one tentacle here, is 0.45 centimeters. So in total, the body of the coral is about 1 centimeter long. So this does make it so right now we're working within the biologically relevant parameters for these actual corals. So now that we've gone over some of these background, we can actually get into the coral kinematics and fluid flow. In this video here, we can see the kinematic motion from one of our coral simulations. And then this video shows the resulting fluid flow. The red arrows tell us the velocity fields that occur from the pulsing of the corals. And here we can see that when the coral is contracting and moving in this upward motion, our velocity fields are also moving in an upward motion. But then when the coral starts to expand, so moving back down, the velocity fields also start to go downward. Looking at our vorticity, which is shown by this blue, we get some sense of how the fluid flow and mixing is occurring. So one of the things that tells us is that we're always having continuous mixing near the coral. We also see, though, that we start to get these vortex rings. So that's this little donut that appears above the coral. And what that does is that tells us that we have a continuous upward jet, so continuous upward flow, even when the coral is expanding or contracting. And that is a little bit less expected. So that's really good to see that we're still getting this mixing occurring even when the coral is moving. In addition to looking at the full 3D simulation fluid flow, we'd also like to look at 2D slices of the full 3D simulations. So since the coral is axisymmetric, we can look at the slices along the tentacle and along the gap to get a full picture. So this video here shows our velocity fields taken from a slice along the tentacle. And again, we're seeing similar to the last video where when the coral is contracting and moving up, our velocity fields are moving in that direction. And when it's expanding, the velocity fields are moving down. Now, what we'd like to do with this are to create these Poincare maps, which are seen in this figure here. Now, these were created by Mateo Santiago for 2D corals previously. And what I would like to do is expand this to the full 3D coral and the 2D slices of the full 3D simulation. And what's really neat about these mappings is that they give us a quantifiable number of how much fluid mixing is occurring. So we start by looking at our stable and unstable manifolds, so these red and blue lines. And if a fluid particle starts along the stable manifold, it will be pushed towards the coral. But if a fluid particle starts along our unstable manifolds, so this blue line, it ends up being pushed away from the coral along this path. And we can use these manifolds then to create our capture and escape lobes, where the capture lobe tells you how much fluid is brought into our region of interest near the coral. So how much fluid is captured. And the escape lobe tells you how much fluid is pushed away from the coral. So pushed out of our region, how much fluid escapes. And what we're then able to do is get an exact number that tells us the area of our interior region and our capture lobe and how much fluid is actually entering our region. So again, I really want to emphasize that this analysis is really unique and special in that it lets us get these quantifiable numbers. So like I've said, currently we're conducting fluid flow mixing analysis just along the biologically relevant parameters. But what we would like to start doing next is actually varying these parameters around biologically relevant values. So the next step is to start running simulations and doing these analyses where we're varying our Reynolds number and our resting time ratio to give us some sense of what's happening around these other values. And I would just like to take a second to acknowledge and thank my advisors, Shilpa Khatri and Ramal Marsha, as well as all of my collaborators, Matea Santiago, Brittany Leathers, Kevin Mitchell, Gabrielle Hobson, and Laura Miller. And finally, I would like to thank my funding sources. So I'm fully funded through the Department of Defense Smart Scholarship for Service program. And additionally, we've received these NSF grants to help us run simulations and do some of this work. Okay. Thank you.